list of examples for outer order execution. So the first thing we'll do today is go through our example in the exercise. I just upload this exercise on Canvas. So if you go to File, basically you will see something similar to this. This is no, not this one. This one. So this is the question on the exam that I gave to my student at TTGS. So the question that you'll be getting will not exactly be this hard, but it's going to be something potentially something similar but easier. The reason why I use this is it shows how out of order execution works given the data flow graph right here. Basically, I'm gonna start to dive into the question. So can you see the question from your screen? Basically, can you read the text and is that big enough for the font? All right, awesome. So for those of you who are here, this is the question, potentially something that is a fair game. Not exactly fair game. This is a little bit too hard on your exam. I'm gonna definitely, if I do something along this line, it would be easier. But this is a question about auto processor. Here are the assumptions. Processor is fully pipeline. Whenever I say it's fully pipeline, it means that let's say I say multiply take 5 cycle. Those 5 cycle is also pipeline. Instruction n, let's say instruction n is in the second stage of the multiply. Instruction n plus 1, if they are doing the multiply, they can be in the first stage. So that's what it means when you have fully pipeline. It has fetch, decode, execute, and write back. There'll be magically no load and store to reduce the complexity of the question. Fetch take 1 cycle, decode 1 cycle, write back take 1 cycle. The processor can only do 2 things, add and multiply. Both adder and multiplier again are fully pipeline. Oops. Add instruction take 3 cycles. Multiply take 4 cycles. And again, similar to how we said last Wednesday, there's a common data bus which allow the adder and multiplier, whenever they finish, they'll broadcast. Who need this value, take it. So that's what the common data bus is for. Instruction always first allocate its own instruction inside the reservation station. What is a reservation station? Is that thing in the decoder that store what are the possible instructions you can dispatch. This is done in a top to bottom order already sorted. Suppose this is the program you want to do. Suppose this is a program you want to do. The first task of this question is essentially, given that table, fill in what are my 5 instructions. Fill in what are my 5 instructions. Should I do one of them and do together do the rest of it, or what's work best for all of you? So let me do one of them. If you look at this data flow graph, what is the first instruction? the add, right? The add to R5 and R6. And I'm sorry, for some reason, my wireless internet decided to drop a lot of packets. I just saw that my screen already moved up, but it takes so much time. That's why I was waiting. So the opcode is what? Add, right? Add. What is the destination based on this data flow graph? What am I adding and what am I producing? Basically, you add R5 and R6, right? So R5 and R6 become source 1 and source 2. What is the result? Do I write it in which one? R1, R2, R5, R4, or R6? What's my destination? R1, yep. Because I say R1 right here as the output from my add. What would be my second instruction? What would be my second instruction? So that's multiply, the second multiply, and the add. Do I do 1 first before 2 and 3? Okay, so yes, multiply. Which one? 1 or 2? It's actually number 1, right? The reason behind that is the multiply number 2 has to wait until multiply number 1 finish before you can proceed to do the second multiply. So this is multiply. Destination is R2, right? Because it's this one. You are multiplying R1 with R6. And the third line, with this table, you know it's something that has to do with R1. So what is that instruction? Is it multiply or is it an add? It's actually an add because the multiply. Oh, no, my bad. It's a multiply. Yes, it's a multiply. It's a multiply. You are multiplying R2 and R1 and you produce R4. Everyone with me so far, right? Then the rest are basically follow from the top to bottom. You have the add. The add takes in R4, R2 and R5, and then you produce R4. Okay? Afterward, the last instruction is the multiply. You multiply what into what, and what is the last one? The last one is weird, but it's a totally legit operation. What am I multiplying with, and what is the result of my multiply? Yep, is you multiply R4 and R4, write it back to R4. Right? So that's it. That's the first part of the question. The second part is basically this. Your next task is to fill in the state of all the reservation station, RAS, which is the register aliasing table. Pipeline stages when you are running at cycle number 9. Use F for fetch, D for decode, EN to specify the end cycle of the execution. So in the adder, there'll be E1, E2, E3. For the multiplier, E1, E2, E3, and E4. W to specify write back. Here is the snapshot at cycle 9 right here. What happened right there? All right, so I'm gonna transfer over the code we just had onto the left here so that we have the code to work with, right? What we do is add R1, R5 plus R6, and then you multiply R2, R1 multiplied by R6, then you multiply again R4 by R2 multiplied by R1, and then you add R4, you basically add R5 plus R2 into R4, and then the last one is multiply R4 by R4 and R4. So this is the same code in part A. This is the same exact code in part A. Let's do this one step at a time. Let's do this one step at a time. All right. So initially, in the first cycle, let's assume that everything is valid. In the first cycle, you can use all the register, right? The tag R0 is going to be R0, this is going to be R1, R2, R3, R4, R5, R6, and R7. And the value is whatever R0 has, right? Basically, these are the initial state. All right, so everyone with me so far. This is instruction 1, instruction 2, instruction 3, instruction 4, and instruction 5. In the first cycle, what happened? What happened in the first cycle? What happened in the first cycle? You fetch instruction 1, right? That's the only thing happening in the first cycle. So let me ask the next step. What happened in the second cycle? Fetch and decode. Instruction 2 is being fetched. Instruction 1 is now being decoded. So when you are decoding, what we assume is when you decode, you add that instruction into the reservation station. There's a one for an adder, another one for the multiplier. Which one are we adding for instruction 1? Instruction 1 is the add, right? It's the add. So in the reservation station for instruction 1, right, you are adding what into what? You are adding R5 and R6, right? So you put in here instruction 1, you add R5 and R6. What are the value of R5 and R6? You basically look here, right? What are the tag and what are the values? The tag and value of both R5 and R6 as well, right? And these are valid. Basically, you copy whatever you see in the register aliasing table. And that's it for cycle number 2. That's all. Next, before we finish cycle number 2, what does the add modify? Which register does the add modify? What's the destination of my first instruction? you are modifying R1, right? So in here, the last thing, one more thing that you have to update is R1 no longer is valid because my add modified that. So I'm gonna say this is not valid. If you want this data, look at tag A. The value is something unknown because I haven't finished my add yet. Right? I haven't finished my add yet. Let's do one more cycle. Instruction 1 is going to be the first cycle of execute. Instruction 2 is decode. Instruction 3 is being fetched. Right? When you decode instruction 2, what do you have to do? You go and look at instruction 2 is a multiply, right? So you go here, station for the multiply, because we said that everything is done during the decode stage. Valid or not? Actually, let me erase this. At this cycle, what are we modifying? We are modifying R1 and R6, right? Our code here say we multiply R1 and R6. You look at R1, basically over here. You now look at R1 and R6. Is R1 valid? Is R1 valid? It's not valid. What's the tag for R1? A. Yep. So you write in A, the value, because it's not valid. I don't even know the value. Is R6 valid? It is, right? Because if you look here, it's valid. The tag is R6, value is R6. That's it for cycle number 3. One more thing that we need to update. We need to update what? We need to update what? I just circled it for you. We know that this modify R2. So in the register aliasing table for R2, you need to get it out, right? Because you know that the value after this point, the value would correspond to this entry X. I don't even know what the value that is, so it's not valid. Any questions so far? Any questions so far? Yes, that's a great question. And yes, this is what has been implemented in your hardware. Exactly something similar to this. On your CPU that you buy, it would have a table similar to this to keep track of these valid bits, the tags and the value. And in reality, this table is a little bit bigger. You're looking at like 64, 128, or 256 entry for the reservation station, so that you can keep fetching a lot of things. All right, any other questions? Okay, so in cycle number 4, what happened? This go into the second stage of execute, right? Can I execute instruction 2 in cycle number 4? Can I do the multiply? If you want to check if you can do the multiply, check if this tag is valid or not, right? So if not valid, it means that you cannot do the multiply yet. Empty. Decode, right? During the decode, now you put instruction 3 in my reservation station. What is the instruction 3? It's a multiply. It's multiplying R2 and R1, right? It's multiplying R2 and R1. So what is R1 and what is R2? A and X. Yep. So you put in here A, not valid. You don't know the value yet. Not valid as well because R2 right now is X, right? So it's not valid. All right. Awesome. And then what do we have to update in the register aliasing table? You are modifying R4, right? You are modifying R4. So you go to R4. R4 is no longer valid, right? The valid bit becomes 0. What is the tag for R4? The tag becomes Y, right? And this is not known. That's it for cycle, oh, and I forgot to fetch. That's it for cycle number 4. In cycle number 5, execute stage 3. Can I do this yet for instruction 2? No, because you haven't finished execute 3. So you still cannot do this. You cannot do this. You then decode instruction number 4. Instruction number 4 is adding R5 and R2. So you're going to look into R2 and R5. R2 first, not valid for R5. The entry is, oh, my bad. Not valid for R2 is X. You don't know the value. It's valid for R5. The value is R5. This add modify R4. This add modify R4. So what do we do here? Because it's modify R4 again, right? You go to R4. It used to be Y. Now my instruction again modify R4. So instead of Y, B now takes the current value. You don't know it. But the tag becomes B. The tag becomes B. And then you fetch the last instruction. In cycle number 6, you are writing this back. This means that instruction 1 is done. What's the tag for instruction 1? What's the ID in the reservation station? A, right? A is done. So what do we do here is basically the hardware would yell out loud to everyone who needs A. Who needs A? And who needs A here? You look at all the table. First of all, you would then go to this reservation station and spot there are 2 A's here. Right? There are 2 A's here. So you're gonna say, hey, this become valid. These two things becomes valid. The tag now becomes R1. And the value becomes R5 plus R6. Same thing goes with R1 right here, right? Because you now have the value. You replace A with R1 again, right? But the tag here, you can keep it at A, it's fine. And then this is R5 plus R6. Basically, you just update the value and update the valid bit. Update the value and update the valid bit. Can I execute instruction 2? The answer is yes. Why is that? If you look at instruction 2, which is right here, everything becomes valid. So you can execute. E1. Start the multiply. Can I execute instruction 3? Can I start executing instruction 3? This is instruction 3, right? And it's not valid yet, so you can't do this. You also cannot do this. And you can decode instruction 5. So if you want to decode instruction 5, you look at instruction 5, it's R4 multiplied by R4 result. Put the result in R4. You look at R4, right? You say, okay, it's not valid, tag is B, you don't know the value. Not valid, tag is B, you don't know the value. Then you say, I'm writing the result back to R4. So you're gonna erase these things. Not valid, put in C. And this is not some value that you do not know, right? Next cycle, cycle number 7, execute 2. You cannot do anything here. Then execute 3. You cannot do anything here. Cycle number 9, at cycle number 9, you execute 4, right? You can't do anything here. When you finish that execute, you're not writing it back yet, so everything here stays the same. That's the answer for this question. Any question that you have about this? Any question do you have? Otherwise, I'm gonna continue on and finish this whole thing, the whole table. Yes, the result, once you're in the write back, that becomes usable. Basically, once you are out of the execute stage, you can use it because you know the result. This is data forwarding, basically. It's instantly available because you forward the data back. Otherwise, you need to wait until write back finish. Okay. So let me continue on to finish this execution. Is it okay? Basically, we'll keep going to finish this 5 lines of instructions. The next part in cycle 10, this is write back, obviously, right? You finish instruction 2. Instruction 2 is the multiply. Instruction 2 is the multiply. It multiplies and write the result into R2. Basically, then the common data bus would yell out loud saying, hey, who need X? This is the value. So you can erase this. Draw it here. 1 is still X. The value is basically R1 multiplied by R6. So this is going to become R5 plus R6. Right? So that's R1 multiplied by R6. This is valid. Still, this is X. This thing is going to be R5 plus R6 multiplied by R6. You can now execute instruction 3 E1, right? Because the reason behind this is instruction 3 is a second multiply. Second multiply need X, but now you have X. So you update here as well, right? Valid X. This is going to be R6 multiplied by R5 plus R6. Can I do instruction 4? My next question is, can I also start instruction 4? Instruction 4 is the add, right? It's correspond to B right here. Is everything valid? Is everything valid? It is, right? So you can also execute the add at the same cycle because you use the adder for that. Instruction 3 use the multiplier. You can do both of them in parallel. Too bad for instruction 5, you're still waiting for B. I'm gonna just write in execute 2, execute 3, execute 4 right here, execute 2, execute 3. Over here, you write back. For instruction 4 has to wait because you want to write back in order. So these are waiting for the write back here, right? When you write back instruction 3, that modified R4. Instruction 3 is Y, right? Instruction 3 is Y. Basically, it goes search who needs Y. At this point, anyone needs Y? Do you see anyone that needs Y? No one needs Y, right? And on top of this, because the way we do this out of order execution, you don't have to do in order write back anymore. You have the value right here. What you can do is to write back instruction 4 again over here right away. Basically, it says who needs B, and you see that C needs B. So you're gonna update this part and say this becomes valid. This becomes valid. This is B. This is B. And what is B? B is whatever value this becomes. Basically, this both of this becomes 5 plus 6 multiplied by R5 plus R6. So that's B. Then you can start execute it right here. Execute 1, execute 2, execute 3, and write back. And write back. Then at the end of the day, at cycle number, oh no, that's the multiply. So it should be execute 4 afterward. Execute 4 and write back. So once this is done, you know the result of C. So you're gonna write the value right here. 1, and let's say this value is like T. So this is basically T multiplied by T. Okay, so this is how you proceed through the out of order execution. You notice a couple of things, right? Write back doesn't have to happen in order now. You don't have to maintain in order write back. The reason behind that is the physical register, the register as you know it, will have the in order retires. What you keep track in the renaming table or the register aliasing table is the new version of your code, so you don't have to maintain that order. Write back can happen earlier, so future instruction can take advantage of it and run it right away. So that's the first benefit. The second benefit is you can dispatch the instruction whenever both the valid bit becomes 1. So that's it for the example. Any questions before basically we go through the review? All right, so these are the topics that would go into the midterm. Here is this basically like a refresher for all of you. It is a lot of topics we covered so far. Lecture 1, we talk about what is the ISA? What are the trade-offs? how does a decoder work? So this is basically assignment 1, right? How do you write a decoder? How does the assembly code get translated into 1 and 0? How do you translate 1 and 0 back to the assembly code given the ISA specification? Von Neumann versus data flow model. For lecture 2, we talk about single cycle architecture and how do we process instruction, right? We talk about different types of instruction, compute, memory, and control flow. Compute is add, multiply, anything that deal with computing. Memory is anything that deal with getting the data from DRAM. Control flow is to branch or jump. How to measure performance. Lecture 3, we'll talk about multi-cycle architecture. This is almost going into pipelining. We also talk about pipelining. Oh, this is not lecture. It's week 1, week 2, week 3. Basically, my bad. Week 1, week 2, and week 3. Basically, we talk pipelining trade-off. Then we talk about data hazard, method to deal with data hazard and data dependency, data forwarding. And then we talk a little bit of superscalar processor. Superscalar processor is when you want to fetch more than one instruction per cycle, want to decode more than one instruction per cycle, want to execute more than one instruction per cycle. Then we talk about the branch prediction, right? The cost of branch misprediction. What is a 1-bit predictor versus 2-bit versus the 2-level predictor? And then we talk briefly about different method to handle branches. Then we talk about the reorder buffer and then out of order execution. This lecture can be on the exam, right? Whatever would come next that are related to the memory and memory hierarchy will be on the final, but not on this exam that's coming up. I'm gonna post the sample of not your exam, but it's a last year exam for the graduate class. Please take a look at that. It will be easier for sure. It will be easier than those exams. I don't have a sample exam for this version of the class because this is the first time I do it, but I guarantee you it will be easier. But if you go through that and you have questions, those are good. Those are probably good topics to take a look at. And if you're confused, let me know because on Monday we'll go through some of those. On Monday we'll go through some of those. Right now, basically before we leave today, do you have any questions that you want to ask? On the topics we covered so far. Basically, anything I can help break down. Basically, next Monday we'll go through in-class exercise, and then we'll cover some of the sample questions aside from the out-of-order execution. Basically, what I'm going to post is basically these exam, right? And you see other questions. You have seen already this question, the ISA question, right? And as I told you, there's a bug here. This thing supposed to be A0000, A000. That would terminate the program. And with this, I am going to also have things like branch prediction question. Just be aware, it's not going to be this hard. And then you can see this out of order execution question that we just went over. This one won't go onto your exam. This is dealing with load and store. We haven't covered that. We cover it after the midterm. So if you look at this and you have questions, we will discuss it on Monday. One more thing, assignment 2 is out. Basically what I want you to do is do pipelining. And you don't have to do data forwarding. Basically, just implement the stalling version. If you have data dependency, stall your code. This should be pretty simple. I then realized that some of you are at a pretty dangerous phase for assignment 1, right? There is a high chance that some of you might not have finished assignment 1. I give you 4 weeks for assignment 2. Basically, you have the entire 4 weeks to work on it. I then add the extra credit for data forwarding. If you want to challenge yourself, try implement pipelining with data forwarding. This would worth 50% more of the assignment 2 grade. Basically, if you screwed up assignment 1, this is your second win. If you choose to start late and did not finish assignment 1, finish it and make sure you do the extra credit. This is almost the same as you did not mess up assignment 1. You can still get a really good grade. All right. So extra credit is something I definitely recommend everyone to try. It's 50% of your grade. Again, that's also a checkpoint. And this time, checkpoint is not extra credit. This is 10% of the assignment grade. So be aware, please start early. I make it your assignment grade because I want to make sure you start early. I was disappointed actually for some of you who somehow panicked in the last week of the assignment when it's due. My regret is I know the assignment 1 is not straightforward. So at least it would be good to panic in the first week of the assignment release, not the last week, so I can help accordingly. All right, so that's it for today. Do you have any questions? Because the rest are pretty much driven by you. If you have questions, we're gonna keep addressing them until the end of the lecture. And I guess I assume we don't have to go to Discord because there's only a few of you who can make it to this class. But I'm gonna keep the recording going on in case you have something related to the topics that I showed earlier that can go into the midterm. This is a great question. Electronic sensors has to do with, so let me actually, do you mind if I create a new slide, like a blank slide so I can draw things for you? So basically, if you look at electronics, right, a lot of them has to do with sensing, right? You have some like real world environment, right? This is real world. And these are basically, think of it as a chunk of data that you're sensing, right? So the sensor would take this data, right? And then somehow, right, this is basically sensor that convert your environment into data. This means that there has to be some data processing, right? Basically process your data. Right? So how many of you deal with things like Raspberry Pi? Yes. So how many of you deal with things like Raspberry Pi or Arduino that has the specification that has register inside? So this thing is the processor actually, and this thing, if you look at say Arduino, for example, if you haven't seen those, basically these are the embedded processor. It's a small computer. It's a small computer that process your data. Most low power processor would have something that is resemble of your in order, like something like 5-stage pipeline, right? And this 5-stage pipeline sometimes is actually 3, 5, 7 stages. It's a low number of stages. What it does is you would then look at the specification, right? If you deal with the Raspberry Pi, for example, you see it's an ARM processor. Arduino, for example, it's called Atmica, I think, processor. It has its own ISA, right? Which means that it also has its own things like register files. It has its own way to manage the memory, right? These process of moving the data to the processor over here, there are two common interface. There are two common interface. The first interface is data. It writes onto the main memory. You write the data to the main memory that you sense. Basically, you sense the temperature, you sense the picture. Those writes to the main memory, and then your processor read this and process it. Basically, if you look at this full-blown like way to process sensor information, the sensor deal with the physical sensing, send the data over to the processor. The processor you have is what we learn actually. It's things that we learn in this lecture. And then the way you interface, as I said earlier in the lecture 1, right? You put the data in the main memory and you read it, process it, produce the output. So what we learn is more like the core of how you build a processor to process these data. One more thing that I want you to be aware of, these days when you look at IoT devices, if you look at low power devices, more and more and more and more are actually dependent on architecture techniques, because the reason behind that is because if you want to optimize for the absolute best case for performance and for power, you need to also modify the hardware. You need to be able to modify some of the hardware to lower the power consumption, to increase the performance, to increase the throughput. How many of you heard of neural processor in Apple iPhone? The one that they claim they can do machine learning. There's a special chip that do machine learning. Yes, no? Oh, so if you buy an iPhone, they also have a special chip. I think they call it neural processor, but basically it's a chip that is designed to do matrix multiply. So a lot of machine learning is basically involved with convolution and matrix multiply. So they built a chip for that. And generally, if I understand correctly, because sometimes I don't really like dive into some of the secret of that, but my guess would be the memory DRAM become the common interface that these processors go take the reads the data, process the data, and spit the data back out. Right? A lot of system on chip. System on chip is basically you have the CPU, you have a full system: CPU, GPU, modem, sensors, way to create an output. Those are called SoC, or system on chip. A lot of these system on chip relies on special hardware that we provide, right? we as in architects and circuits people, right? We come up with the design circuits, look at our design, cry and yell at us. Those are impossible. Then we fix the design and make it possible. Then the great people in the circuit area would implement it for us. Then people in the system community would build a kernel, build a system that works on it. So everything is related. That's how I would phrase it. Especially in this case, you have physics people that deal with sensor. You have low-level device people who make the sensor. Then there's the circuit people who built the actual circuitry. We, as an architect, provide the high-level design. System people take it and make sure it can run the program. And then compiler people would then make sure the code compile and optimize the assembly for low power, for example. So hopefully that answers your question. Does it? Or I'm not sure. It's kind of like yes and no. Like everything is related in a sense, and you can't just take out one area and say, hey, magically we'll come up with the design. Another common thing that I can kind of like tell you what we do that becomes a product, right? How many of you heard the news that, hey, Apple phone, like iPhone, for example, would make your phone slower to save the battery without telling you? It made the phone a little bit slower to save the battery. Have you heard about those news? So I can tell you that this is a basic trick that happens in every single processor. We call this, it's called DVFS. Let me pen. This is called DVFS, dynamic voltage frequency scaling. What it does is, let's say you buy a 3.4 gigahertz processor, right? You can actually operate that in a 3.4 gigahertz clock. But the ability that we have nowadays for the CPU to change the frequency to make it faster or slower, to change the voltage from say 1.5 volts to 1.2 volts, right? These things impact energy consumption. Think about it this way. Let's say you know you have to run a marathon, right? The 22 miles. You probably don't want to sprint because you die in the middle of that 22 miles, right? The same thing with the battery life. You know that. So how long do you typically use your phone until you charge it? Assuming normal use, not playing like games, many hours, right? 6 is actually it's too small. I would say the expected value would be like 10 hours, 12 hours. To be on a safe side, maybe 24 hours. You know that amount of, you have the certain amount of battery, right? So what happened is, as you use your phone, the battery age, it means that you can't fully charge them. What Apple is doing is it knows that your battery degrades to that certain amount. So it knows that you can't maintain that many hours of active use using the same frequency. I can reduce the frequency and I can reduce the voltage to make it last the whole day. These are the design options. I think the lawsuit is more like because Apple did it without telling you. Let me tell you this. Every single CPU does this. Is this the real reason why all phones slow down? So actually there are multiple reasons. That is potentially one of them. The second main reason is if let's say you update the iOS, right, into say version, what version is it? Actually, I forgot to keep track of what. It's I would say that's not their intention for sure, but it might sound like that. What happened is as you change the architecture of your chip, as you change the architecture of your chip, sometimes you add things like special instruction to run things quickly, right? there might be special instruction to do matrix multiply, for example, in the new phone. What can happen is the older phone that you're using, they don't have those instructions. So what the compiler is doing is it would compile the code so that it use from the same program, it would use a different, less efficient instruction, right? Which means that you're gonna feel slower for sure when the iOS update, because the newer version would try to use the new features. When that happens, you also feel like older phone is slowing down. Another thing is as you pack more and more things in the software, like iOS, the software that used to support new devices, like a new Apple Watch, right? These software become clunky, and sometimes this thing is just burning power or slowing things down, even though you're not using it in the old phone. So those can happen too. So there are multiple reasons. One reason is maybe they change the frequency without letting you know. Sometimes it's just the system software are built for a new hardware, and they virtualize some of the old things. So when they virtualize those, uh, the number of instructions you have to run increases, so your phone becomes slower. So that's another possible explanation. So hopefully these things combine. Hopefully now you have a little bit more, I guess, insight into why sometimes the phone slows down, especially when you update to the new OS, right? Uh, and occasionally you see the OS version that they claim they clean things up. Usually those are performance update. They clean things up to make sure things becomes a lot faster. Yeah. And to be honest, I think you might even feel like this is a bigger problem with Android phones. The reason behind that is you notice the hardware manufacturer, the OS manufacturer, and the software manufacturer are totally different companies. So sometimes they don't talk to each other as well, right? In Apple, they own the hardware, they own the software. So sometimes it's actually more efficient. Sometimes there are features in the iOS that are like, this is fast, and in the Android world, even though they are open source, right? So you might have cool features that are coming out, but it might be working for certain phones, certain CPUs, but it works not as well as the other certain group of phones. So those can happen too. So yeah, but I mean, I'm sure Apple would like be happy if they can sell more phones too. So I'm not sure if if the accusation is correct or not. I just don't want to make any judgment. All right. Any other questions? I mean, these are good discussion. I love it that you have these questions, because I would like to be able to tell some of the story that I learned, or some of the speculation that I feel like this is what they do, right? And as I said, I think I said it like multiple times. Like I want to change the like everyone, at least like people in Asia, aspect of like architecture. There are fun things to do, and fun things that you can do in hardware that can be pretty cool, right? Uh, if you know what you're doing. If you don't know, everything becomes a black box, essentially. Okay, so if you don't have any more questions, I'm gonna keep being online on yes, after this class could be potentially design an Arduino processor. I mean, if you don't mind learning a hardware description language, what you learn here, you can build your own processor. If you're curious, you can join. Like, how many of you heard about RISC-V? RISC-V. So RISC-V is an effort by a group of researchers from the university that some of these people actually are behind the design of MIPS, the one that you are designing right now. RISC-V is we call it Open ISA. Open ISA means that these are the specifications and you can use it without any copyright issues. There's actually a bunch of company in hardware nowadays that take this specification and modify your hardware, like or come up with a new hardware that is based on RISC-V. So the motivation behind this whole RISC-V things is a lot of professors in architecture now realize that there are certain area in architecture that you come up with your own hardware that becomes limited because you ended up with talking to Intel, talking to ARM, talking to NVIDIA, talking to these companies that don't want them, they don't want to give all the information to you. So like, you're so sick of this, let's come up with this open ISA that if you want to come up with cool hardware, use this ISA. It's also fine. So you can run a real program similar to MIPS, right? You can run a real program. This is newer, so it's actually optimized for like modern program. Then you can come up with your own hardware. Another thing is called HDL. HDL stands for Hardware Description Language. Basically, it's a CS people would hate me that if I said that's a programming language because it doesn't program. It's a language that describes the hardware. Then you write your own hardware in this language. Then you use a different program that perform a layout. It will actually give you pretty much almost like a circuit level layout. And then you can implement this hardware in things like FPGA. If you want to go even further, you can fabricate the chip given this thing. So if you don't mind learning this new language that describes the hardware, which the way it works is like from the lab that I give you, right? From the lab I give you, the way we treat hardware description language is almost like kind of similar to that. So it's not like a big step, but it's a new language. So I don't want you to learn a new language. If you're curious, let me know. Let me know because there's quite a lot of fun things you can do if you want to design your own processor, but it does take time, right? Especially the fact that you have to learn a new language. Yes, you can design your own processor. After this class, I want everyone here in this class to be aware of the fact that if you're sick of the hardware, you can design your own hardware. There are a group of people in the world whose job is to come up with a new hardware, mine included, right? That's my job. One thing that I always like, I think Ajahn Kanat and myself joke about, right? Because he was like a theory guy, right? He's like high performance computing. He's really like good at building software. So he was joking that he would treat the hardware like a god because he cannot change it and he'll build the software based on that. And then in my case, I'm treating the software like a god because I cannot change it. And then I build the hardware to conform to this thing. In reality, we change both. And so, yeah. Sorry, I ended up talking for a long time with that one question. Okay, so that's it for the class. I'm gonna unshare my screen, I guess, and post the slides. Hopefully it's not too confusing for the rest of your friends on this particular one slide. And let me stop the recording. Okay.